Now that we understand entropy and information gain, let us see the decision tree algorithm. Now it will be very easy for us to understand the whole algorithm of decision tree, how a population is considered and split into different segments, so that each segment is really useful to take any business action upon. So the major step is to identify the best split variables and best split criteria. So how do we actually find out those variables which will split the whole population into segments that are pure, basically segments that can be acted upon easily, segments that can be classified as, yes, this is a buyer segment, yes, this is a responder segment. So that way, so once we have the split, then we can go ahead and segment level. At each segment we can actually further drill down, so we can start at the root, segment it out, and then each segment can be taken again, it can be drilled down based on the same criteria. So the whole algorithm of decision tree in coding language or usual algorithm manner, if we see, start with leaf node or start with the node, and then find the best splitting attributes. There are many multiple attributes. Find the best splitting attribute. How do we find the best splitting attribute? Based on the information gain. For each attribute you calculate the information gain. The one with the highest information gain, obviously that is the best splitting one. So for example, in this case, we'll calculate the information gain for age, we'll calculate the information gain for gender. Looks like gender has a better information gain. Yeah, gender wins when we compare age and gender. So that's how we compare two attributes. So that's how we find the best splitting attribute, by comparing information gain across for all the attributes. Split the node using the attribute. So once we finalize the attribute, then you split the node into uh, two segments, so you have the whole population. So out of all the variables, you calculate the information gain and find the best splitting attribute, and then split the node based on that best splitting attribute. Let's say if gender is the one, then you will have male and you will have female, so that is how we split the node. Now go to each child node, so go to male and then repeat the step 2 and step 3. That means again you consider rest of the variables. Now gender is anyway gone. Again, if you consider rest of the variables, can we split it further to make it more pure? Can we split this further to make it more pure? We continue, keep on doing that, so that we can finally arrive at few segments, and we already know their characteristics. Let's say if there is a segment here, we know its characteristic, it is male, and then later on whatever variable is chosen, based on that we can find out the characteristics of that segment, finally whether that is a good segment or bad segment based on the output that it is giving, or sales segment or responder segment, or bad by loan defaulter segment, etc. So we start with the root and then we segment it out based on the splitting criterion, that is information gain. Once we split it, again we repeat step 2 and 3 and continue further. Now when do we stop? So we keep on doing this, and each leaf node, the one each leaf node, finally we reach to a position, there is only one element left. That means there is no further splitting possible. So that is one way, that is one criteria which we can stop. Our algorithm runs out of attributes, so there are only two attributes. So gender is the first one, age is the second one. That's it, we are done. We don't have any other attributes, or maybe 3 attributes. After that there are no other attributes. That's where we can stop. Or no further significant information gain. This is important. So even though there are attributes left, even though there are some more, each of these segments have enough number of samples, but there is not much of information gain. So here the entropy is like the even by splitting it, we are not gaining much of the information gain, and impurity is still remaining the same, then there is no point in expanding the tree, because we are not actually gaining any additional information from there. So in that case also we can stop. So each load contains examples of one type, or algorithm runs out of attributes, there are no further attributes, or there is no further significant information gain, then we can stop the decision tree algorithm. So that is the overall decision tree algorithm, which is used for customer segmentation. We take the overall population and divide it into segments. Let's take an example to understand the decision tree algorithm in a better way. Let's start with the data set that we have taken. There are 14 observations, a simple data set. We have variable called gender, we have variable called marital status, and ordering the product or not. There are customers who are going to order the product or not. So overall there are 14 customers. Okay, the 4 customers have ordered the product, 10 customers haven't ordered the product. Okay, now there is a variable called gender, okay, which is male and female. Out of gender, male 7 people ordered, 3 people, 1 did not order. Female 3 ordered, 3 did not order. Similarly, there is marital status. So which attribute to consider? First, shall I split the whole population by gender, or shall I split the whole population by marital status is the question. So simply we calculate the information gain for gender, information gain for marital status. The one with the higher information gain should be given the first preference of split. So there are two variables. The one with higher information value need to be given the first preference for splitting. There are two variables here, gender and marital status. Let us calculate their information value. So for gender, the information value entropy before the split minus entropy after the split, or the average entropy or the weighted average entropy after the split. So entropy before the split is 86%, so 4 positive 10 negative. 86% is the impurity at the root level. So entropy for gender equal to male at that split, there is a 54% entropy impurity. There is a 100% impurity at gender equal to female. Now similarly for marital status we calculate the each node level entropy. Now information gain for overall gender is information or the entropy before the split, impurity before the split, that is 86%, and entropy after the split. So the weighted average is 8 divided by 14 into 54, that is the individual node entropy and the node weightage. Node weightage can be found from out of 14, 8 are male, so node weightage can be found from number of items within that node, so that is 8 by 14. So 6 by 14 is female node weightage. So the information gain is entropy before the split, that is 86, minus entropy after the split. So overall information gain is 12. So for gender the information gain is 12. Similarly when we calculate for marital status, for married entropy is 0%, impurity is 0 because it is very pure segment, all of them are negative, and for unmarried the entropy or the impurity is 72%. So information gain for marital status is 86.3 minus information the entropy after the split. So the information gain for marital status is 60.5. So marital status has higher information gain, which means marital status need to be given higher preference, which means the first split attribute should be marital status. Or out of these two, which one should be given higher preference for splitting, that is marital status. Similarly we take we will consider the whole population, then we start splitting it based on marital status, so married and unmarried. So because marital status has higher entropy, if required we will further do the drill down for each of these root or child nodes. Again we go ahead and do another split. If it is not required, then we can leave it at this point. This is already pure, all the married customers are negative only, so 9 people are married, all of them are negative, there is no further drill down required here. If there is a requirement, then we'll do it, or we'll not, we can leave it at that point, but the process remains the same. We take the segment and we consider all the attributes. The one with the higher information value should be given higher preference for splitting up the whole population. So once again the decision tree algorithm, you select with a leaf node. At the beginning the leaf node is the root itself, the first node itself is the leaf node, and find the best splitting attribute. We calculate information gain for all the attribute. The one with the highest information gain is the best splitting attribute. Split the nodes using that attribute and then go to the child node and repeat step 2 and 3 again and again. That means once you have the leaf node, you have the best split already taken, then after splitting you will have the child nodes. Once you have the child node, go to each child node and see further best split attribute, then split it. So we repeat the process of splitting again and again. So when do we stop? Whenever there is no further examples, or when there no further records in a particular segment. When the algorithm runs out of the attributes, there are no further attributes, and then there is no further significant information gain. Just by splitting we are not achieving any information gain, then there is no point in going ahead, so we can simply stop it there. Till now we have seen variables of the type binary outcomes. Let us say if we take gender, male or female, we were very comfortably splitting the whole population into two groups, you know, a male population, female population, and we took one more variable called income or marital status, which is high, low income, marital status, married, unmarried, etc. But our age also we divided it into uh, young and old. But what if we have multiple splits for a possible for a given variable? Let us suppose there is this variable income which takes 5 values: very low income, medium income, high income, very high income. So sometimes we can have variables which are taking multiple values, so just splitting the population directly into two segments might not be possible. So we have, we can split it into 5 segments, or we can split the same into only 4 segments. Maybe we can say very low income is one segment, but remaining three are three different segments. That is another option. Or we can even split that into just 2 segments. So very low income, low, medium, these three are one segment. High and very high income are one segment. So we can split the population just for one single variable, which is income. We can have multiple splits. Earlier there was one variable, there was only one split, there was only one information value. But if the values of the variable are taking, if the values that are assumed by the variable are more than 2, then we may find multiple information gain values. So basically that will lead us to multiple split options. There will be multiple scenarios, and then we'll have multiple split options, and each of them will give us an information gain value. So what is the true information gain for income? So if you take 5 segments, then you will have one information gain value, let's say that is I1. Now when you just divide it into as 2 segments, that is like low, very low and medium income is one segment, and high, very high is other segment, then we will have information value I2. So there are multiple options, as that's what we were discussing about, like population can be divided based on income. Very low is segment 1, medium is segment 2, very high is segment 3. So that will give us an information gain value. Now population can be divided into just 2 segments, that is very low income, and then remaining everything in one more segment, that is low, medium, high and very high income. That will give us another information gain value. Similarly, there is one more scenario. So there are multiple such scenarios that can be we can find multiple such scenarios. How do we actually find the information gain for this type of variables? It is simple. So for income, we'll consider all the possible scenarios, not only these three, all the possible scenarios that can be done based on its variable. For each scenario we will find the information gain out of all these. So let us say for this scenario information gain is I1, for this scenario information gain is I2, for this scenario information gain is I3. Similarly, there are multiple scenarios, we'll find multiple information gains. Out of all those information gain values, the best information gain value is the actual information gain for that particular variable, and that particular split is the best split for that income. So this is split 1, type 1, this is split 2, this is split 3. So the split that gives us the best information value is the best split for this particular variable. So in the decision tree algorithm, we not only need to find the best variable, we also need to find the best split within that given variable. So we need to find the best splitting attribute along with the best split rule as well. So our algorithm for decision tree will slightly modify here. So we'll select a leaf node, we'll select one attribute at a time. For each attribute we partition the node population and calculate the information gain. So we consider all the scenarios and we find the best split criteria. then we will have the information gain for that particular variable along with the best split criteria, and then we do the same thing, the same information gain calculation for all the variables. So at the end of it we'll have best splitting attribute along with best split rule. Once we have the rule and the attribute, so that we have the variable, let us suppose income, and we also know whether we need to divide it into low, very low versus remaining, or like we know the split criteria also. Once we have the attribute and split criteria, we split the node using the attribute and the criteria. Again we go to the child nodes, repeat the step 2, 3, 4 again and again until we reach the stopping criteria, which is each leaf node has no further records to further split. Algorithm runs out of attributes, there are no further attributes or no further significant information gain. So that is what we do when there are many splits possible for a single variable. This is a very usual scenario that we might face. So this is the decision tree algorithm full version. So let us see how to build a decision tree on R. So we are dealing with a data set called e-commerce customer survey data. So there is a survey conducted for a set of customers and then asked whether they are finally satisfied or dissatisfied with the product or not, and then what is the order quantity that they have ordered, what is the region, etc. So there are several attributes. So we need to find out, we need to build a decision tree and find out the concentrated satisfied and dissatisfied customer segments. Can we actually find out the characteristics of customers who are satisfied? Can we find out the characteristics of the customers who are most dissatisfied, so that we can later on take some actions on these customers who are dissatisfied, or similar kind of customers who are dissatisfied when we see the same characteristics, and similar kind of customers when they come later on, if they are, can we guess whether they are going to be satisfied or dissatisfied. So let us build a decision tree to find out the customers who are most likely to satisfy, most likely to dissatisfy later on. So the data set is e-commerce customer survey data. I have already imported it. So it has customer number, which region the customer is from, what is the age of the customer, what is the order quantity, what is the customer type, what is the improvement area. Since this is a survey data, so the customer has been asked whether what is the improvement area that is required on the website and the e-commerce side. What is the overall satisfaction, whether he is satisfied or dissatisfied. Now what are we trying to find is, are these customers mostly from west or east that are very much dissatisfied or satisfied? Are the young customers very satisfied or dissatisfied? The customers who are ordering high or low, I mean, are they the ones which are satisfied or dissatisfied? What are the actual characteristics of the customers who are most frequently dissatisfied, or what are the characteristics of the customers who are most likely to be satisfied? So that is what we are trying to do by building a decision tree. So the code for building a decision tree, here is the code for building a decision tree. So we need to use a function called rpart. It is a part of a library or a package called rpart. So we need to use, first we need to attach a package called rpart. So rpart contains the decision tree building library. Then once that package is attached, then we are ready to build a decision tree, which is using the function rpart. Now what we are trying to model is our dependent variable is overall satisfaction, which indeed depends on region, age, order quantity, customer type, either any improvement area, etc. Method equal to class. So this indicates that our dependent variable is of the type yes or no, 1 or 0. It's a class variable. Here it is satisfied, dissatisfied. It is not continuous variable. There are other type of trees where we can actually have a continuous variable, but here we are doing a classification, and our objective variable or our dependent variable is a class variable. That is why we need to mention method equal to class, data is dataset name, and then there is one more parameter that we are also passing on, that is control equal to r part control min split equal to 30. What does this mean exactly, min split equal to 30? Now in this decision tree, if you remember, what we are trying to do is we take the overall population and divide it into uh, bins, or divide the whole population, split it into sub segments, subsets. So if we keep on subsetting the data, and then if we reach a point where the final leaf or the final node subset has only 30 elements, what we are telling here to R is, when you see any node which has just 30 elements, do not go further and subset it, just stop it there. Why we are asking that? Because here what we are trying to do while subsetting, so when we subset, we are also finding out the characteristics. That means we are seeing, let's say, we can subset. One example of subsetting is all the customers who are from north region, all the customers who are from south region. So we can have two subsets like that, and whether north region customers are highly satisfied or south region customers are highly satisfied. Now to draw such conclusions, if we don't have sufficient number of records in that particular node, then it doesn't really make any sense. Even if we are saying north region customers are highly satisfied, but there are only 4 or 5 customers who are from north region, whereas south region customers there are like in 10,000, then it doesn't really make any sense to compare north versus south, because it doesn't have any significant number of customers who to actually draw that conclusion. So that is the reason why we are saying the node size, or when you split, the size of the segment should be minimum 30. If it is going less than 30, do not go ahead further and segment it out, just stop the segmentation there. That is what we mean to say by control r part control min split equal to 30. We can set it as 40, 50, it is depending upon us, but generally we can split it, we can set it as 30. There are around 11,000 customers here, so we will have enough number of segments. So now we will try to build the tree, e-commerce tree, that is built. Now we can see the output. This is the output of e-commerce. It is saying at the root level it is giving some values, and then 2, 4, 5, 3. So it's not that easy to read out here. So a tree diagram, if we draw from this whole tree, then it will be easy for us to read. What we can do is we can use rattle package, install rattle package, and then try to draw a plot. Rattle package, then fancy rpat plot. We can draw a plot, and then we can see what exactly this tree is built of and what exactly these numbers are. So at the root there are 11,812 customers. Out of them 5401 customers are satisfied, 5401 customers are dissatisfied, and remaining customers are satisfied. So that is why that whole what do you call, the whole node, root node is classified as dissatisfied. So to start with, we have more dissatisfied customers, less satisfied customers at the root level. Now when we go to, at the root, what is the first variable that is splitting the whole tree, that is starting the split, that one is order quantity. So out of all the variables, region, age, customer type, improvement area, order quantity is the one which is coming as best split when order quantity is less than 40, when order quantity is more than 40. when order quantity is less than 40, yes, then we have to come to the left hand side. When order quantity is less than 40, then there are, so we have to go here. When order quantity is less than 40.5 actually, so when the order quantity is less than 40.5, there are 7,000 such customers where order quantity is less than 40.5. Out of them, 1027 are satisfied and remaining are dissatisfied. Out of 7,000 customers, 1027 are satisfied, remaining are dissatisfied. Now let's try to understand what exactly this tree means, the output of this tree. So we have built the e-commerce tree, and what exactly the output means, it is showing as one root and then some number, and then there is one more number, and then what exactly that segment is. If you look at this carefully, the way we should read this output or the tree output is this. It shows node and then one parenthesis. So this is first node, second node, third node, fourth node, fifth node. You can see that in the graph. First node, second node, so this one, whatever are the details here are from second node. This one, whatever details are here are from fourth and fifth nodes. Fourth node, fifth node, because after second node there is a split of fourth and fifth node. That is the reason why after second node, fourth and fifth subnodes within second node, which are again subnodes within first node. Now third one is another subnode within first node, and it has no further subnode. So that is what node means. And what exactly is the split? How do we define the split? The split on the left hand side is order quantity less than 40. Yes, this is one. This is the one with order quantity less than 40. Order quantity less than 40, no. That means order quantity more than 40 is split name. Then within this, the split is s greater than or equal to 30. That is the split, fourth one. Fourth node represents the split age greater than or equal to 30, which actually it is exactly 29.5. So age greater than or equal to 29.5 is the fourth node, and then age less than or equal to 29.5 is the fifth node. That is what split indicates. Then n, how many items are there, how many records are there within that split. So at the root level there are 11,812 records. That is the overall number of records within the data set. And then in the second node, this node, how many records are there? 7,000 records are there. So if you see here, 63% of the records fall here. So out of 11,000, if you calculate 63%, there will be 7,000 records. So each node, how many items or how many records are there in that node. Age greater than or equal to 29.5, that is this node, fourth node. How many records are there? 652 records. Fifth node, age, oh sorry, it's not 652, it's 7025. So there are 7,400 records in this one, second node. There are in the fourth node there are 7025 records. In the fifth node there are 379 records. You can see that this is the fifth node which has 379 records. Again in the third node, this node has 4,408 records. Okay, these are the number of records. Then loss. What is loss? We are considering this whole segment as dissatisfied. If you come to root, there are 54% dissatisfied customers, 54% dissatisfied, remaining all are satisfied. And we are saying this root is this node is dissatisfied node. That means purely it has to have all of them dissatisfied, but there are still some satisfied customers. So that is a kind of loss to that node. Like it is defined as, you know, counter to that whatever definition we are giving. So that is defined as loss. So if this node is dissatisfied, loss in that node is number of satisfied customers. How many are there? 5,041 customers. Remaining all are dissatisfied customers. So they are around 54% dissatisfied, 45% satisfied. That is why this node is actually termed as dissatisfied node. Now in this node, again second node is also known as, termed as or decided as dissatisfied. Why? Out of 7400, loss is only 1027, so almost like 86% are dissatisfied, 13% are satisfied. You can see this here. Y probability is in the bracket, so Y takes two values, dissatisfied and satisfied. So this is dissatisfied percentage, this is satisfied percentage. Dissatisfied 54%, satisfied 45%, dissatisfied 86%, satisfied 13% in this node. Dissatisfied 90%, satisfied 9%. So you can see that here, out of 7025, 90% dissatisfied. That means almost 7000 or 6300 are dissatisfied, remaining 650 are satisfied. That's why this whole node is termed as dissatisfied. Out of that dissatisfied node, what is the loss to dissatisfied? Okay, within this fourth node, what is the loss? That 9% is the loss for the statement that we are making, or the against our statement. With the number of loss, like the number of items that are contributing to loss is around 652. The value of y predicted, y val, is dissatisfied, so that is what y val is talking about. And y probability, so dissatisfied probability is this much, and then satisfied probability is this much. This node, fifth node, is termed as satisfied actually. So y val is satisfied, and what is the loss? 4 is the loss. That means 375 are actually satisfied. Dissatisfied are around 1%, around 98% are, or 99% are satisfied. You can see this here. First value shows dissatisfied, second value shows satisfied. Again, when you go back to the last node, the node, first one is node, that is third, and the split is order quantity more than 40.5. This is yes, so this is no. So order quantity more than 40.5, 4400 customers are there, that is n size of this one. 4400 out of 11812 is around 37%. You can calculate that. Out of overall population, what is the size of this particular node? People who are satisfying this condition, out of overall population, people who have ordered more than 40.5, how many such guys are there? Around 4400 guys. And what is the y val? This whole set is classified as satisfied. You know why? Because there are 99% satisfied, around 1% only dissatisfied. That 1% constitute to 34, remaining all are satisfied. That is how we read this output. Again, it is all clearly mentioned here, and star denote the terminal node. Terminal nodes are 3, 4, 5 and 3. 4, 5, 3, they are terminal nodes. That's what the output is telling us. Overall number of elements are 11,812. So how do we validate the decision tree that we have built? Okay, to validate the decision tree, we can make use of the data that is already used in building the decision tree. Imagine, let us take an example of this data set that we used for building the decision tree. We have the region, age, order quantity, customer type, etc., and final overall satisfaction, whether customer is satisfied or dissatisfied. Now this is the actual value. Now when we substitute region, age, order quantity, customer type, improvement area, etc., all these values in our decision tree for prediction, then decision tree will be predicting this particular observation as one class, whether it is satisfied or dissatisfied. Now there is some predicted value, there is some actual value. This is the actual value which is dissatisfied, and if our predicted value is again dissatisfied, then our tree is doing good for this observation. And if the predicted value is satisfied for this particular observation, that means our decision tree made a mistake for this particular observation. Now if we repeat the same for each and every observation, we know what is the output class, we know what is the resultant y value. But what are we doing? We are acting as if we don't know that value, and we are trying to predict the same value. So there are some actual values, there are some predicted value, and wherever the actual value is satisfied, we want to predict it as satisfied. Wherever it is dissatisfied, we want to predict it as dissatisfied. Now when it is satisfied, if we are predicting it as dissatisfied, now that is an error, that is a misclassification error. We want to reduce those misclassification error as much as possible. We want to increase the accuracy. That means whenever it is satisfied, we want to actually predict it as satisfied. So if you look at this confusion matrix, what is a confusion matrix? So if we understand confusion matrix, or if we look at confusion matrix closely, we can see that there are two classes, that is positive or negative, 1 or 0, or satisfied or dissatisfied. These are the actual two classes. Now there are two more there are two classes that we are predicting, that is positive and negative. So when we have the values input into the model, the final output or the predicted output will be again positive and negative. When the actual value is positive, we want to predict it as positive. That is like the actual condition is positive. Now it is that positive condition is truly predicted as positive. That is called true positive value or true positive cases, and we want to have as many as true positive cases as possible. When the actual value is negative, we want to predict it as negative, so those are called true negative cases. So whenever it is positive, we want to predict it as positive. Whenever it is negative, the actual value, we want to predict it as negative. So for a good model, we want to predict only positives as positives, negatives as negatives. Now when the actual value is positive and we are predicting it as negative, that means that is an error. When the actual value is negative, we are predicting it as positive, that is also an error. Those are false positives. When the actual value is positive, when we are predicting it as negative, those are called false negative values. Now those are misclassification errors. So for a good model, we want to see false negatives and false positives almost equivalent to 0, and true positives and true negatives, whenever each negative value is classified as negative, we want to see them as almost 100%. So the accuracy is nothing but the ratio of sum of true positives and true negatives divided by the total number of observations. So out of all the observations, how many times we have actually classified positive as positive, negative as negative. So we want to actually have accuracy as 100%. What is misclassification rate? It is simply false positives and false negatives. What is the percentage of total false positives and false negatives? Or it is simply 1 minus the accuracy. So that is how we validate the tree models. Whenever we have classified using tree model, and if we want to get an idea on how much is the accuracy of our model, we can look at the classification table or confusion matrix and get an idea on the accuracy of the model. Now let us find the accuracy of the model that we just built. So e-commerce tree is the model that we built. The actual values of the output are satisfied and dissatisfied. Out of overall 11,812 observations, how many observations we have accurately classified, be it satisfied or dissatisfied, how many observations we actually misclassified. So let us do the prediction. So we use predict function to do the prediction. So I'm using predict function, predict using e-commerce tree, type equal to class, the output I want it to be class as satisfied or dissatisfied, and I'm storing the predictions in e-commerce prediction and another object. So e-com prediction is my new object. So let me see the predictions. Like for each observation, they're satisfied or dissatisfied, satisfied, dissatisfied. Those are my predicted values. There are 11,812 observations, so R has shown us first 10,000 observations, not a problem. So that is the predicted class. What are the actual values? The actual values are nothing but they're there in the data set, right? So we have the data set. In that, the row or the column overall satisfaction, overall satisfaction. Now that those are the actual values, these are actual values. We have the actual values, we have the predicted values. We just need to create the confusion matrix. The confusion matrix is can be created by using table. So I have a function table. I'm using predicted values and the actual values are e-commerce customer survey. In that data set, the overall satisfaction is my actual value. I have predicted values. I'm just keeping them in the form of a table, and this whole table I'm storing that in confusion matrix object. So now I'll try to print this confusion matrix. This is the confusion matrix. Okay, when the actual value is dissatisfied, we are predicting it as dissatisfied 63 times. When the actual value is satisfied, we are predicting it as satisfied 4749 times. When the actual value is satisfied, we are wrongly predicting it as dissatisfied 652 times. So our errors are, misclassification error is 652 plus 38 occasions total misclassification, and classification or the accuracy is it looks really high compared to the errors that we are making. So let us calculate the accuracy. So from this table directly, the accuracy can be calculated from that table directly in the confusion matrix. First element first plus the fourth element, that is 1 1 plus 2 2 divided by sum of all the elements, or simply we can write 11,182. That is the accuracy value. And what is the accuracy here that we have calculated? Around 94.15%. That is the accuracy of our model. 1 minus accuracy is our error. Around 5%, 5.8% is the error that we are making in this model. 94% is the accuracy. So that is how we validate the tree and find out the accuracy. How do we find the accuracy? You use the tree and build the predictions using the code predict. Using the function predict, we can make the predictions. We can make the predictions using the function, and we just took the tree and we made predictions for all the data points, and then we have the actual values. Then we have created the confusion matrix. From the confusion matrix we can calculate the accuracy.